Welcome back. The last video we were discussing about applications of Laplace transform. Started with solving ordinary differential equations, first order and second order we have done. In this video we will start with looking at solving system of linear equations. So let me do the general second order. We do the second order linear system. So let me take the general system. So how do we solve this general system of equations, linear system of ODEs. So how do we solve this? So let me solve this 2 by 2 system. Dx1, x1 and x2 are two variables as a function of t. Let us see a11 x1 plus a12 x2 plus b1 of t. Another equation is dx2 by d2. So x1 x2 are two dependent variables and t is the independent variable. So you have 2 1 x1 plus 2 2 x2 plus b2 of t. So a1 a2 all these are constants. So you can put this in an equivalent form, that is d dt of x of t, which is equal to matrix, just say, let us say A is a matrix 2 by 2 matrix with these constants, and you have x of t plus b of t. So where A is where x of t is a vector x1 of t and x2 of t, and then A is matrix a11 a12 a21 a22, and then b of t is a vector, that is b1 of t b2 of t. So this is the system of two linear equations. First order equation for vector, first order linear ordinary differential equation for a vector. So how do we solve this? Because the t is positive, you can apply Laplace transform. So solution procedure is to, if this is general equation, general system, this is 2 by 2 system. So procedure is same for any order, any n by n system also, any order, nth order system. If you consider, that means you consider n linearly independent, n coupled ordinary differential equations for x1, x2, xn. The procedure is same. So let me outline the procedure before we solve some problems. Let us apply Laplace transform, application of Laplace transform to the equations. Give, application gives. So what are those? You apply these two equations, you apply Laplace transform. So dx1 by dt, that is if you apply, that is s x1 bar minus x1 at 0. So at 1 x0 is not known. So this is the system with the initial value you have to provide. That means x1 at 0 is, let us say, let me give this as x1 0, x2 at 0 is x2 0. So here so the system is this with initial, this is the equation, the same initial values. If you consider x at 0 is actually the vector, that is x10 x20. So these are the initial values which you have here separately. Here is a vector initial value vector. So these are the initial values, initial values. So those initial values you can use here when you apply it for the first equation dx1 by dt, for which Laplace transform of this, which is equal to a11 x1 bar, that is the Laplace transform of these are functions of s, and then plus a12 you do not apply. So you apply even x2 of t, you apply Laplace transform, that becomes x2 bar of s plus b1 bar of s. Similarly, you apply to the other equation. So, you get instead of this x 2 bar of s minus you have x 1 at 0 is x 1 0. So, let me replace this as x 1 0. If you do it here, this is x 2 0. This is equal to a 2 1 x 1 bar of s plus a 2 2 x 2 bar of s plus b 2 bar of s. So, this is how I applied and I used the initial values. Okay. So, this gives me x 1 bar of s. You write it as a system. So, this is a system for unknowns x 1 bar of s and x 2 bar of s. So, if I put it together as a coefficients, this coefficient of x 1 bar of s is s minus a 1 1 and you bring this on this side as x 2 a 1 2 x 2 bar of s is equal to x 1 0 and you have this, you bring this x 1 0 here plus b 1 bar of s, that is the right hand side. Other one is x 1 bar of s, you bring it this side. So, you have a to 1, you bring this, take this other side. So, that will give you minus or rather let me write this, you bring this this side. So, you get this one minus plus here s minus a 2 2 times x 2 bar of s. This is equal to x 2 0 plus b 2 bar of s. So, this is like a system s minus a 1 1 minus a 1 2 minus a 2 1 s minus a 2 2. This is the system matrix and you have x 1 bar of s, these are the unknowns, x 2 bar of s, and this is the right hand side that is known, that is x 1 0 plus b 1 bar of s. You know what is b 1 of t. So, you know it is a Laplace transform. So, x 2 of 0 plus b 2 bar of s. So, this vector is known. So, it is like you are looking for this. So, you can get the solutions easily and I write directly using this method x 1 bar of s and x 2 bar of s is I think Cramer's rule that goes like this. So, this will be like, so let me write if you use that directly, what you do is x 1 bar I write directly, this is so in the denominator you have a determinant of this matrix, that is determinant of s minus a 1 1 minus a 1 2 minus a 2 1 s minus a 2 2, and here the same determinant you consider, but replace first column with right side column. So, that is first column I am replacing with x 1 0 plus b 1 bar of s, x 2 0 plus b 2 bar of s, and this other column as it is. So, that is a 1 2 s minus a 2 2. So, this determinants if you consider, that is exactly a solution x 1 bar of 2. Similarly, x 2 bar of s you can get this as first matrix is first column as it is, that is s minus a 1 1 minus a 2 1, and this will be x 1 0 plus b 1 bar of s, x 2 0 plus b 2 bar of s, the second one, and this determinant is a matrix determinant, that is s minus a 1 1 minus a 1 2 s minus a 2 2 here, and we have a minus a 2 1. So, these are the solutions you can get like this, and you invert it, inversion gives x 1 of t and x 2 of t, that is the solution you are looking for. Okay. So, let me do some example. Example is let me solve some system of equations, solve solution of this system dx by dt, which is equal to ax with x at 0 equal to 0 1, and then where a is a matrix 0 1 minus 2 3. So, how do we solve this? Let me use you can use directly Laplace transform. If you use directly, you can get first equation is, you write equations are dx1 by dt So, x is x of t, which is x1 of t and x2 of t. So, x1 of t which is equal to, this is x2 and dx2 by dt as minus 2x1 plus 3x2. So, these are the two equations you have, and the initial conditions are x1 0 is 0 and x2 of 0 is 1. Apply the Laplace transform. Laplace transform gives s x1 bar of s minus x1 at 0, that is 0. So, I do not use 0, which is equal to x2 bar of s. Other one is s x2 bar of s minus 1, which is x2 of 0, which is equal to minus 2 x1 bar of s plus 3 x2 bar of s. So, put one into the other or you solve directly. So, you can get x1 bar of s as if you try to solve these two equations. So, this is equivalent to getting s 0 s minus 1 times here x1 is bring it this side. So, you get 2 and this is s minus 3 of x1 x2. This is the system. So, here you get 0 and here you get 1. So, I consider non-homogeneous system here because there is no non-homogeneity here. So, in the general case you have the non-homogeneous term, that is b1 b2, that is b of t is not 0 here. So, follow the same procedure and get this. So, you can get this as x1 x2 as determinant. If you look at this determinant, s square minus 3s plus 2, and then here the determinant of 0 1 you put it here and minus 1 s minus 3. So, that makes it 1, that is simply 1 here. So, you get this one, and x2 bar of s is again, so denominator is same, and the numerator the determinant of replace 0 1 here and this you keep as it is. So, you have simply s, that is simply s of that. So, if you apply this, use the partial fractions and write this as s minus 2 minus 1 by s minus 1 will give me this. This one you can write 2 divided by s minus 2 minus 1 divided by s minus 1. So, that I get these two are same. Okay. So, inverse Laplace transform gives x1 of the solution. 1 by s minus 2 is e power 2 t and then minus e power, and then x2 of t is 2 times e power 2 t minus e power t. So, these are the two solutions which you can these are your system. So, this is the required solution. Solution satisfy the initial value is here. Okay. So, this is how you solve the system. You can also follow the same procedure and try to solve system of second order equations. For example, let me do this example, one more example. You can also follow the same system, second order system of ODEs. Follow the same procedure and you can work out. For example, you have, let me use d square x1 by dt square minus 3x1 minus 4x2 equal to 0, d square x2 by dt square, and then you have plus x1 plus x2 equal to 0. So, this is a system. This is valid for t positive. x1 and x2 are the unknowns, x1 of t, x2 of t are unknowns. You need to know its initial value because it is the second order. You need to provide x1 of 2, x2 of t at 0. So, let me give the initial values at 0. These are 0 and this is 1 initial values, and you also have dx1 by dt at 0, which is, let me give as 2, and similarly dx2 by dt at t equal to 0, this is, let me give as 0. So, these are the initial values, initial conditions, and these are the system, this is the system. So, You can reduce this also as a system of 4 by 4, it is like 4 by 4 system you can convert with an unknowns x1, x2, x1 dash, and that means dx1 by dt and dx2 by dt. So, these are with these unknowns you can make a system of first order system. Okay. So, this is this as your new x, this is your a, that is there is a procedure to make that. Okay. So, you assume x1, x2 and you use this as your new variable, some y1, this you use new variable y2, and so that you y1 dash is from the equation, y2 dash from the equation, but from x1 dash is nothing but y1. So, that gives the matrix. So, x1 x dash is equal to you can write like this way. So, 4 by 4 system, because there is a 2 by 2 second system of equations of second order. So, you have 4 equations of first order you can make, and that way also you can, that is equivalent. You can equivalently you can get first order 4 by 4 system, 4 by 4 couple equations. Otherwise, you can directly apply anyway t positive, you can apply Laplace transform. The solution is by Laplace transform, apply Laplace transform to the equations. We get what we get is so if you apply the second order derivative, you get s square x1 bar of s minus s times x1 at 0 and then minus x1 dash at 0. So, that is dx1 by, so basically I have to write dx1 by dt at 0. So, these are the things you have to use. So, because of this x1 0 is 0 and dx1 of 0 that is 2. So, I will replace this with here 2 and here this is 0. So, that makes it minus 2 here, which is plus equal to 3x1 minus 4x2, 3x1 bar of s minus 4x2 bar of s, this is equal to 0. So, this is one equation. Other equation also you can apply the same procedure for x2. So, you have s square x2 bar of s minus x2 of 0 s times x2 bar of 0, that is also 0. So, I do not write this here, and then x2 at dx2 at 0, dx2 by dt at 0 is, that is also 0. So, you do not have any contribution here. So, you have plus x1 bar of s plus x2 bar of s, which is equal to 0. So, if you write them together, so as unknowns, x1 bar of s is s square minus 3, and then x2 bar is 4 times x2 bar of s, which is equal to 2, and here x1 bar of s plus 1 plus s square times x2 bar of s, which is equal to 0. So, you can get your x1 bar of s as a determinant of this one, which is s square minus 3 minus 4 1 plus s square. So, this is if you actually calculate, it is going to become what you get is write directly as s square minus 1 whole square. The numerator, so you have 2 0 here and here minus 4 1 plus s square. So, you have 2 in 2 times 1 plus s square. So, this is 2 times 1 plus s square. So, this is my x1 bar of s, other one is x2 bar of s, denominator is same s square minus 1 whole square. And numerator, this is derivative, this is the determinant of 2 0, you put it here in the second column, and you write the first column as it is, that is s square minus 3 and so on. So, you have minus 2 comes up. Okay. So, this if you make partial fractions, I write directly partial fractions, you can make a partial fractions here with s minus 1 whole square and s minus 1 whole square and s plus 1 whole square. So, with this if you make the partial fractions, you end up getting the first one as 1 by s minus 1, that is coefficient is 0, square term will be there, and then similarly you can get this s plus 1 coefficient is 0, but 1 by s plus 1 whole square coefficient is 1. So, this sum is actually same as this, and this side you will get all the terms that contribution. So, half of 1 by s minus 1. So, the coefficient of 1 by s minus 1 is half, and also other one is also minus half is the other coefficient of 1 by s minus no, this is what you get is minus 1 as s minus 1 whole square, and then minus half is 1 by s plus 1 coefficient, and then you have I think this is minus half, here also minus half, okay. And then last one that is coefficient of 1 by s plus 1 whole square, which you will see as minus half again. So, this is how you factorize partial fractions you can get, and the inverse Laplace transform. Inverse Laplace transform gives the solution x1 of t as 1 by s minus 1 square, that is e power t, because of square t into e power t, and then other one is e power minus t because of s plus 1. This is also square. So, you have t times e power minus t. So, you can see this as e power t plus e power minus t as the solution. x2 of t is also you can get the half times e power t minus half times t e power t minus half times the third term will give e power minus t, again minus half times t times e power minus t. So, if you simplify it, you have half is common, e power t minus e power minus t, and then minus half t by 2 times e power t plus e power minus t. So, this is exactly your the solution x2 of t. So, this is how you can get your solutions. So, this you can also write this as sine hyperbolic t, and this is cos t times minus t times cos hyperbolic t. So, this is simply 2 times t cos hyperbolic t. So, this is how you can get your solutions of your equation that satisfies these initial conditions, all these 3, okay, all the 4 initial conditions, you can get your solution like this. This is how you solve the system of linear equations, linear ordinary differential equations, whether it is a 2 by 2 system or any system, I mean 2 system, 2 equation system or n equation system. The procedure is same, though it may be lengthy to use the Laplace transform, try to calculations may be lengthy, but the procedure is same. Also for second order or higher order you can follow the same procedure, because you know the derivative, any nth derivative you can apply the Laplace transform, you know the procedure, use all the initial conditions and then simply solve the linear system and invert it, get the solution. These differential equations, linear first order and linear second order equations, you will come across in many applications. For example, when you look at harmonic oscillator, model for harmonic oscillator, if you look at it if you put it in a free medium, there is no resistance. If you do not consider the resistance, you will have a first order second order equation, and with resistance you will have one more term, first order term you can add to the second order equation, second order differential equation, and of course initial conditions you provide, and basically whatever the system, whatever equations we have solved, you end up for this harmonic oscillator in a free or a resistance medium, so that you can once you solve it, you see that depending on the by forcing. So, if you have a forcing term in your system, in your harmonic oscillator in the model, because of the forcing, if its oscillator is moving, and if it's done by the forcing is done by a harmonic oscillator, initial that's the forcing is harmonic, then you can get some kind of resonance. Resonance can be overlooked by damping term, that is by including the resistance medium. So, if you keep the resistance in the system, you can avoid the, if you keep the resistance in the system, the harmonic oscillator system, you can avoid resonant frequencies. So these things in this basically basic physics, you come across these kind of problems. You solve the second order linear equations. If you are an electrical student, if you see current and charge in electric circuit, that is you will see that the model equation is a first order linear ODE that you can solve by Laplace transform. And also not only just the circuit, you can have a network of the circuits, so that you have a coupled system of equations, first order equations. That is where you come across these kind of differential equations, ordinary differential equations, which you can solve by Laplace transform with this initial data. Okay. So these are the applications you find in this physics and electrical engineering for the ordinary differential equations. Let me solve before we close this ODE. You can solve similar ordinary differential equation with the initial conditions or boundary conditions. You can solve many of these problems. You can solve by Laplace transform technique. So let me solve some special equations. For example, Bessel equations also you can solve, which is a second order. The procedure is same, but we will see how we use initial value theorem and final value theorem in the process of solving this second order differential equation, ordinary differential equation. So let me solve this. Solve Bessel equation. It's called Bessel equation. So let me write what it is. You have a t times d square x by dt square. The second order equation with the coefficient as being t, and then I have a dx by dt, and then plus a square t times x. X is a function of t, so it's basically function of t is equal to 0. You have this initial conditions. So I provide initial condition here, that is actually it is a second order. So you have initial condition x at 0 is equal to 1 bounded, and you should also provide x dash at 0. So for the timing, let us choose some value. Okay, for any value, let us see what you get. Okay. So how do we solve this? So how do we solve this equation? Solution. Again, so this t is positive, so you apply the Laplace transform. Domain is positive. Laplace transform gives application of this Laplace transform for t variable. For x of t, if you apply, so this t times you apply the Laplace transform of t times d square x by dt square, and then you have a Laplace transform of dx by dt that we know already, and you have this Laplace transform, a square is constant, t times x of t, Laplace transform, which are functions of s, which is 0. Okay. So this is equal to, and if you have seen earlier as the property of the Laplace transform, we have seen this is actually minus dds of the Laplace transform of d square x by dt square, and this is as it is. So you can write directly as x bar of s minus x at 0. X at 0 is 1. So you have this is a x at 0, so that is value is 1. So I write for this plus a square. This is t times x of t is again minus dds of Laplace transform of x bar of s. Okay. So that is I am applying the same technique here, which is equal to 0. So if you actually do this, this is equal to minus dds of Laplace transform of this second derivative is s square x bar of s minus x at 0, that is 1, minus x at x dash at 0, that is which you have taken as any constant c. Okay. So that is let me write this as c, which is anyway constant, and this is the s into x at 0, that is s into 1. So that is s. This is for this term. Another term is here x bar of s minus 1, and here minus a square dx bar of s by ds equal to 0. So if you actually differentiate this, you can see that this is going to be 2s x bar of s minus s square dx bar of s by ds minus minus plus, if you differentiate that is 1, this is a constant, that is 0, plus s x bar of s minus 1 minus a square dx bar of s or s derivative of it is 0. So, if you actually see this one, you see that this is going to be, you make a minus both sides. So, you have a plus here, this is going to be minus, this is going to be minus, and this is plus, this is plus. So, if you combine this, s square plus a square times dx bar s of ds, and then minus s, this is going to be 2s minus s is s x bar of s, this is going to be plus because of 2s minus s, that is plus s, and which is equal to that is anyway this is gets cancelled. So, you have this is 0. So, what you get is you can directly solve this, because this this is simply x bar of s divided by d x bar of s here. Bring this is separation of variable method, you can solve this, and you have a ds. So, you have minus s by s square plus a square times ds. So, you integrate both sides to see this plus some integration constant. Let us call this a, where a is integration constant. So, what you end up is log of x bar of s, which is equal to this. If you look at if you directly write this is 1 by square root of s square plus a square. If you differentiate this, so you get minus half, and or rather I think if you simply differentiate this, the antiderivative of this is this, okay. Derivative of dds of this, if you calculate, is actually minus half, I think. So, exactly. So, how do you calculate, how do you do this? This is again log s square plus a square, that is the antiderivative. So, you have 1 by s square plus minus 2s. So, you have minus 1 by 2. So, that if you 2 gets cancelled, you have minus left. So, this is the integration of this plus e power or rather let me write this as log a, okay. Log a is integration constant. So, you see that log, if you remove both sides, x bar of s as a divided by this is going to be square root of s square plus a square. This you can write this as, you can put this as a square, okay. So, log a minus this is a divided by this, log you remove, this is what you get. So, a is arbitrary constant, and as you see, and so far although we have used this x of 0 equal to 1 and x dash of 0, which is any number, given any number, the solution is same. So, solution is, so far we have arrived here, still we have an arbitrary constant, okay. A is an arbitrary constant. So, how do I get rid of this? If I calculate x of t antiderivative, I mean inverse transform of this will give me something, okay. So, a times the Laplace inversion of 1 by square root of s square plus a square. So, this is my, which is a function of t. So, this is my solution, but still I have an arbitrary constant here. So, this is where I use this initial value theorem, that is given that x of 0 equal to 1, okay. So, which is equal to 1, this is actually limit of x of t as t goes to 0. This is exactly what we have seen is limit s goes to infinity s times x bar of s by initial value theorem. Initial value theorem that we have seen in the last video. So, what is this one? This is limit s goes to infinity. So, you have s times a x bar of s is a divided by square root of s square plus a square. So, this gives me a times, and you have this is simply a, the limit value is a, because s divided by square root of s square plus a square, limit s goes to infinity, there is going to be 1. So, a is actually 1. So, that means that implies a equal to 1. So, a equal to 1. So, implies x of t equal to Laplace inversion of 1 by square root of s square plus a square, which is a function of t. What is this inverse? To get this inverse, you have to write this. This is actually a special function which is J0 of AT. So, if this is this, you can take it as directly, because J0 of t AT, you consider it's this is a Bessel function J0 of t. J0 of AT is a Bessel function whose Laplace transform, if you calculate, actual definition of J0 of AT is you have this this is a series expansion, that is a square t square by 2 square plus a power 4 t power 4 by 2 square 4 square 2 square into 4 square, okay, and then minus a power 6 t power 6 divided by a t power 6 divided by 2 square 4 square 6 square and so on. So, this is the definition of this special function, special Bessel function of first kind, okay, Bessel function of 0th order Bessel function, 0th order Bessel function of first kind. If you have studied differential equations course, you understand this is a solution of this Bessel equation that we have here. You can get the solution by Frobenius method. It's a series expansion, series solution method. You can get these solutions. So, you can see that this is going to be the value of this J0 of AT. If you actually apply the Laplace transform for this J0 of AT, by definition of your Laplace transform 0 to infinity e power minus st times this, you put this 1 minus a square t square by 2 square a 4 t power 4 by 2 square 4 square and so on. You put it and you have a ds, sorry, this is dt, okay. This is the integration. So, thing is you can take this integration, because this is a uniform convergent series, because this is J0 of AT is uniform convergent series. So, you can take this integral inside. So, if you take that inside, you see that it's you can apply, you can take integration term by term, and you see that each term, if you look at it, that is going to be Laplace transform of 1, that is Laplace transform 1 is 1 by s, and then you have next term is a square by 2 square, Laplace transform of t square is 2 factorial divided by s cube and so on, like that. So, you can go on writing like this, a power 4 by 2 square 4 square, Laplace transform of t power 4 is 5 factorial divided by s power 5, right. This is a power 4, that is, this is going to be 4 factorial divided by t power 4 is 4 factorial divided by s power 5 and so on. So, if you actually see this one, s 1 by s times 1 minus a square by 2 square times 2 factorial divided by s square plus a power 4 by 2 square 4 square times 4 factorial divided by s power 4 and so on. If you write like this, what you see is this as 1 by s times this series is a representation for 1 plus a square by 2 square, a square by s square power minus half. Okay. So, this is how you can get this, and this is exactly what you have. So, this, if you simplify, what you are seeing is 1 by square root of s square plus a square. So, Laplace inversion of this is actually J0 of AT, that is what I am writing directly here. So, if you know exactly what is the solution of this this one, there is another way of, because I know that this is a solution of J0 of AT is a solution, because I know what is J0 of AT, its series, I am putting into this Laplace transform and get this as a Laplace inversion. If you do not know, you can also directly get, you do not need to write this expression. So, this you can think of like calculating this general way of finding c minus I infinity to c plus I infinity Laplace inversion, that is 1 by square root of s square plus a square times e power st ds. So, this is what you have to calculate, 1 by square root of s square plus a square. is having a branch points. So that's that's a different technique you have to exploit. This is a advanced some complex variable technique you have to use, because this s square plus a square is having a branch points which is at minus a to a at both places. Sorry, this is ai and minus ai. So you have a branch points. So in the complex plane, S complex plane, you have ai here and you have minus ai. So this is the cut you have to make, this is the cut you remove. So that is for which you have that is the, if you use this as a cut in the complex plane, and you can choose your C, any C positive, so that all your there is no so you can consider this kind of contour, usual Bromwich contour if you consider. So if you consider this, and also somewhere you have to avoid this. So how to avoid this? You avoid like this, and then you connect these two somewhere here, you go here. So this is how you are going, and you enter here and you come back, you go here and you go in this direction, come here and come here, and then you enter here and then you come back here and join here. So somewhere here I am removing, okay. So these two you remove and make it a single round. So you have a simple closed curve you have. So if you calculate this, the contributions of these branch points will give the value of this integral, that is going to be something equivalent to J0 of at. There is another way of another expression, another way of finding this Laplace inversion, which you may get another different expression for J0 of at, another representation of J0 of at you will get if you do this way. Okay. So because we know these are the solutions from the differential equations, J0 of at whose expression I know, for which if you calculate the Laplace inversion, you can easily see that that is going to be 1 by square root of s square plus a square. So Laplace inversion of this directly, I am writing this as J0 of at. This is the solution of this your equation, your Bessel equation, with the initial condition is this, and is the other condition any other whatever may be the value of the other condition, the solution is this. The solution is simply J0 of at. Okay. So this is how you solve this second order special Bessel type of equation, and if you are given any second order linear ODE with variable coefficients with t or t square, you can apply the Laplace transform and use the similar procedures, try to get the inverse, apply these initial conditions whatever required, and somewhere you are using this initial value theorem or final value theorem, any one of them you can use to get any arbitrary constants involved in your solution. So I will try to do one more example in this, I will try to how to use this initial value problem, initial value theorem, how to use in in solving the second order linear differential equation with initial conditions. This along with other applications, for example solving, we will move on to solve partial differential equations in the next video. We will see in the next video. Thank you very much.